Okay. Let's talk about a couple things and then I will just kind of open the floor up to you guys. Okay. Let's talk a little bit about energy systems. Okay. So first and foremost, right, we got the ATP PC system, right? So we talked about that over there. It's real simple, right? You need more ATP. Phosphocreatine will say, here you go, here you go, here you go, right? You get a phosphate, you get a phosphate, everybody gets a phosphate, right? So that system works for about 1 to 4, 1 to 5 seconds, right? So if you're doing like a 100-meter sprint, vast majority of the energy is going to come from that ATP-PC system. The more you use that system, the better you get at it. So you're going to extend by a couple of seconds. But after that, you start utilizing what's called the glycolysis system and then the electron transport chain. So the electrolysis, with the glycolytic system, you take glucose and you convert glucose into a chemical called pyruvic acid. And then from pyruvic acid, it's converted into a chemical called
Citrate.
well, now citrate's in the Krebs cycle, but before what enters the Krebs cycle? Citrate can enter the cycle, but normally it's starts with an A.
Yeah.
You have nightmares to your
Yeah.
Krebs cycle stuff.
Yeah.
Acetyl-CoA.
Acetyl-CoA.
Right. So you take pyruvic glucose and you convert it into pyruvic acid. This is grossly oversimplifying this, guys. There's like 11 enzymatic steps that happen right here just to go to that, and then there's a couple more that go from pyruvic acid to acetyl-CoA. And there's a whole bunch of stuff going on in the Krebs cycle, discovered by a guy named Hans Krebs. There's also another cycle that works called the Calvin cycle, which works in the opposite direction for plants. It's also sometimes known as the TCA cycle, the trans-carbolic acid cycle, and in Russia it's called something else. So you converted pyruvic acid, super quick, super efficient, provides a small amount of ATP. You'll get about 2 ATP per glucose molecule that gets converted into pyruvic acid. Okay, so moderately efficient, moderate duration. Okay, so what would be examples of sports that are primarily glycolytic in nature? So glycolysis is the primary energy system for activity that's anywhere between 5 and about 30 to 45 seconds in duration. Football? What would be some other sports that are glycolytic in nature?
Baseball.
Baseball is mostly ATP PC, but a little bit of lactic. Same thing with football. Football's mostly ATP, but some glycolytic. What else? Huh? Depending on the event and track, so anything over 100 meters up to about 800 meters. Basketball, soccer, lacrosse, rugby, hockey, right? A lot of, especially like what's going on in a lot of our field sports, right? You're sprinting for a little bit and then you're like, so think about like soccer, right? So, right, you kick the ball, right? Then you run the field, right? You kick it again, right? Might be a little bit of sprinting back and forth, right? So you sprint for what? 20, 30 seconds, and then you're kind of standing around waiting for something to happen. Right? Same thing with hockey, right? You skate down to the other end of the ice, and then you're kind of waiting around for the ball, defend, whatever, stuff like that. Okay. So a lot of our field sports were primarily the lactic acid system, and then some of the track events. So anything over about 800 meters, you're getting more and more into the aerobic system. 1500 is the last like really like lactic system, and then you're getting into like the 3,000 meter steeplechase. It's the dumbest name for an event, steeplechase, because there's no steeple you're chasing. You're just running around. Right, and so then we get into what we call the oxidative phosphorylation system. So that acetyl-CoA will then go into the Krebs cycle. The whole function of that, now you get a little bit of ATP, you get about 2 ATP out of the Krebs cycle, but the whole function of the Krebs cycle is to strip off all of those hydrogens from glucose. So glucose has got 6 carbons and 12 hydrogens. We take all of those hydrogens and they're taken via 2 electron transport carriers called NADH and FEDH, right? So NAD becomes NADH and FEDH becomes FADH2. You remember what NADH and FADH stand for?
The N sounds like nicotinamide.
Nicotinamide, adenine, dinucleotide. you get it from niacin, and then that F comes from riboflavin B6.
Okay, yeah, I remember that.
Okay? So the whole point of this is to strip all of these electrons and put it into here. Who here, has anybody here been to Paterson, New Jersey? You been to Paterson, New Jersey on purpose? Yeah. So while you were in Paterson, New Jersey, you didn't happen to see any of the model recreations of early factories from the beginning of the revolutionary industrial revolution? So the Industrial Revolution in the United States started pretty much in Paterson, New Jersey. That's one of the first factories that were powered by water. If you go to England, you'll see the same kind of a thing, right? So if you go to England or you go to Paterson, New Jersey, I would recommend England over anywhere in New Jersey. So if you go to early, like at the beginning of the industrial revolution, all the factories were on rivers, right? So you have the river, which would turn a wheel, and that wheel would do what? It would power stuff, right? So a water wheel would power things. Same thing happens with oxidative phosphorylation inside the inner inside of the mitochondria. Okay, so all of those hydrogens, which we call basically it's just an electron, get taken from the outside of the mitochondria into the inner matrix of the mitochondria up into the intermembrane space. Right, so we pump all those electrons into the intermembrane space, creating a electrochemical gradient. What have we learned about gradients in nature? Does nature like gradients or not like gradients? Does not like gradients, so it wants to get rid of this gradient. So what ends up happening is, through a process called chemiosmosis, it goes through this enzyme called ATP synthase, which is, anybody been to like Disneyland, right? Turnstile? So it's like a turnstile, right? Every time an hydrogen goes through there, it turns the turnstile. And when it turns the turnstile, an ADP combines with an ADP, or with a phosphate, to make a brand new ATP, right? We call this oxidative phosphorylation. It's the same kind of gradient you have that powers the wheel of an old factory, right? Because how does that work? It's a gravity gradient, right? The river is flowing downstream. As it flows downstream, it turns the wheel. Same thing here. We're just taking the hydrogens downhill. Now, we haven't gotten rid of our hydrogen problem. We've just simply moved the hydrogens from here to here. So how do we get rid of the hydrogens? You see a formula here. 2 hydrogens plus 1/2 O2 gives us H2O water. We call this metabolic water. This is why, if your glasses are dirty, right, you can take your glasses and, right, you can fog up your glasses. You are breathing out that water. We call that metabolic water. This is the only reason you and I and every other aerobic organism are aerobic organisms. We only intake oxygen because oxygen is the final electron acceptor for all of those hydrogens that are part of metabolic processes. This is literally the only reason why you need oxygen. That's its sole function in your body, is to be the final electron acceptor for that. Okay. Now, this process creates a whole bunch of ATP, right? You can create up to 36 to 38 ATP during this process, right? So it's an extremely efficient process, but it takes a while to do, okay? Because you gotta take the glucose, turn it into pyruvic acid, and then the acetyl-CoA, then it's gotta go through the Krebs cycle, and then the electron transport chain and electron ATP synthase, okay? So we've got our 3 different energy systems. So we've got our ATP, our lactic acid, and then our glycolytic system, okay? Why do we have three systems? Why did we evolve to have three different systems? Huh?
To adapt to our environment.
Right, how does it help us adapt to our environment? So where did humans evolve?
Africa.
Huh?
Africa.
Africa, we were, from Africa. How did humans make their living for the most of human history?
Like, how did they get food?
We were hunter-gatherers, right? So we would hunt and we would gather, okay? Well, right, we weren't always top of the food chain either at the same time, right? So imagine you're a hunter-gatherer, you're gathering nuts and berries and fruit, and you're in the savannas of Africa, right? And all of a sudden a lion comes out of the grasslands at you. And the only system you have evolved is the ATP-PC system, which allows you to be highly explosive and quick for about 8 to 10 seconds, right? Lion comes out of the grassland, comes at you, you take off in a dead sprint, and about 7 to 8 seconds later, right, you're gonna time out, lion, hold on, give me a second, right, what's gonna happen to you?
Gonna die.
You're gonna be lion food, right? You've only got the second system, right? Takes about, right, so lions coming at you, right? Right, about 7 or 8 seconds in, then you take off, you gotta go to 30-second sprint, right? Maybe you make it away, maybe you don't, right? Or you only have the oxidative system, which takes a full 60 seconds to really kind of get up and running, right? You're definitely gonna be lion food by the time like your system gets up to run, right? So humans were hunter gatherers, right? So what does it mean to be a hunter gatherer? Hunt and gather food, right? So the gathering part's pretty no-brainer, right? So like shrubs and mushrooms and nuts and berries and all of that. Hunting part, right? So what'd you have to do if you were a hunter? Right? You gotta pack them in, right? And they go hunting. First thing, what do you gotta do? You gotta go look for fresh tracks, which means you're doing what? Sometimes maybe for a couple hours. Just wandering around looking for, hey, those look like fresh gazelle tracks. Then what are you gonna do? You're gonna follow the gazelle tracks, and then what do? You find a herd of gazelles, and then what do? You kind of team up together, right? Okay, right, you guys, right, you run at them, right? And we're gonna bum rush them, we're gonna divert a couple off, and then we're gonna chase it down, right? So, chase it down, right? Right, you kind of try to corner it in, like, you know, or against some shrubs, or, you know, up against a canyon wall, so it's got nowhere to go, right? That might require, like, right, running and sprinting, like alternating around. So you gotta have that energy system. And then finally, you gotta have that burst of energy for the kill, right? So you gotta get up close to the gazelle and, right, stab it hard enough to go in there, right? So we evolved the three energy systems to meet all of those different types of energy demands that we needed to have, right? We are especially good at this system, right? We are the best running species that ever evolved, right? We can run tremendous different distances. To this day, in some parts of Africa, with, you know, some of those you know, tribes that are still, you know, they still, you know, live in bush and teepees and stuff like that, they engage in what's called persistence hunting. Anybody heard of persistence hunting? What's persistence hunting?
It's where you basically outpace somebody by just like walking after it.
Jogging, running, yeah. So basically, they'll literally just run a thing to death, right? So they'll just chase a gazelle for 2-3 hours in the heat, and then, right? So we can sweat. We're really good at sweating. Other animals don't sweat too much, right? How does your dog mostly lose heat? Panting, right? He'll pet sweat a little through his paws, right? You know, same thing with horses, right? They don't lose heat very well. We're really, really good at it. So, right, they're in Africa, they'll literally run a gazelle to death, right? The gazelle will get so overheated and so tired, it'll just lay down and just kill me, right? So we're very, very good at that. So that's due to those energy systems. Okay, let's talk about the different muscle fiber types, okay? So we got 3 different muscle fiber types. got three, as far as you guys are concerned, we got three types of muscle fiber types. We got type 1, known as slow twitch, also known as slow oxidative. We got type 2A, which is fast oxidative, and type 2B, which is fast glycolytic. Slow twitch muscle fiber types don't generate a lot of force, but they are slow to fatigue. Type 2A are kind of intermediate, right? So they generate pretty high amount of force, moderately resistant to fatigue. So like for example, a world-class 400 or 800 meter sprinter is going to have a lot of type 2A. Type 2B is going to be high force production, very low exhaustion time. So world-class 60 meter runner, 100 meter runner, high jumper, long jumper, shot putter, javelin, discus, all of that, that's going to be our type 2B. Now, we can do muscle biopsy, where we actually take a sample of your muscle and we can actually check and see. Some muscles are going to be more type 1, some muscles are going to be type 2. So for example, like some of the postural muscles are mostly type 1 because we don't want them to fatigue because they need to hold you up. The average person, you just take an average sample of people. Most people are going to be approximately 50-50, type 1, type 2A, and type 2B. Right? So 50% type 1, 25% type 2A, 25% type 2B. Which is good, right? Because average early humans, right? It didn't pay to be a specialist, right? It paid to be a generalist, right? You need to have amount of strength, endurance, all of that kind of stuff like that. A small percentage of the population is disproportionately one muscle fiber type over the other. So for example, world-class marathon runners, they might be 70, 80% type 1 muscle fiber types. Okay. World record for men for the marathons, like 2 hours and like 2 minutes. That's like just over a 6 minute mile, guys, pace for 26 straight miles. So, right, that's not a jog, right? They're running hard for 26 straight miles, okay? World-class sprinter like Usain Bolt, world-class shot putter, javelin, they might be 70 to 80% type 2B muscle fiber types, okay? So these are one of the best predictors of like athletic success in particular types of things, right? So for example, if you take the person that wins a marathon, they might not have the highest slow twitch muscle fiber type, but you take the top 10 finishers, they're going to be like 2 standard deviations higher than the lowest person, the slowest person on the thing, right? Now, there's good and bad to being a specialist, right? So if I have a lot of type 1 muscle fiber types, I could be a really good long or middle distance runner, but I'm never going to be super big and super strong. I'm a world-class sprinter, right? I could be big, fast, and strong and explosive, but I'm probably never going to be very good at running for great distances, right? So like Usain Bolt, like no matter how much he trains, every single one of you guys could run a marathon faster than Usain Bolt can. Right? So you guys can take comfort in that, right? But you guys will never be able to beat Usain Bolt, right? Or like the guy that's the best marathon runner. You'll never ever be able to beat him in a middle distance race, but you guys can all probably outlift him pretty easily. So for example, world-class marathon runners, they have about a 10-inch vertical jump. World-class sprinters have about a 35 to 40-inch vertical jump. Right, so that's largely genetic. Now here's the crazy thing. For some reason we don't understand, but if you exercise a lot, type 2B downgrades in the type 2A. We don't really know how that works. That's why sometimes taking time off actually helps you regenerate type 2B muscle fiber types, which are most explosive. We don't really know how that works. So endurance athletes are going to be type 1. So like a rugby player or a soccer player or a hockey player would be predominantly type 2A, and then like a shot putter would be primarily type 2B muscle fiber types. So that's kind of the nuts and bolts there of exercise physiology. Let's talk about a couple other things, and then just kind of whatever. By the way, if you guys have questions, feel free to ask any questions. Let's talk about VO2 max real quick. Who here's heard of VO2 max? So VO2 max is a measure of oxygen consumption or oxygen utilization. It's the single best marker for aerobic capacity, aerobic function. VO2 max is typically measured in milliliters per kilogram per minute. So that's relative. There's also absolute, which takes into account your body mass and all of that. So typical VO2 max range for, like, you just took your average college age girl, right, is going to be somewhere between 26 to about 34 for females, and then about 30 to about 38 for males. That's the average. There was a guy, he was a Nordic skier, cross-country skier from Sweden, had some genetic abnormalities which gave him a higher than average amount of hemoglobin. Off season, his VO2 max was tested one time. By the way, the guy holds like pretty much every record for like cross skiing, like cross-country skiing. Like it used to be like he'd show up for a race and everybody's like, well, I guess I'm going for second place. His off-season VO2 max was reported at 99. It's the highest recorded VO2 max we've ever had.
What does that number mean? Like, I
So,
don't get what the number
He
is.
his body can utilize 99
Oh.
milliliters of oxygen per kilogram of body weight
Okay.
per minute. Now, how much can your VO2 max, your aerobic capacity increase with training? How much of an increase can you get?
A few percent?
Huh?
A few percent?
About 20% is how much you can increase your VO2 max. So, if your VO2 max is 35, you can go up to about 42. So you can get a modest at best increase in aerobic capacity. Which means, right, I take, somebody who's just, so I had a kid came out, tried out for the cross-country team. Never really done sports before, but decided they wanted to try for the cross-country team. We did a VO2 max test on them. They never really worked out much in their life. Their VO2 max was 50. Right, and then we tested them, right? We put them on a training program and we tested them again several weeks later. So what would be 20% of 50? So our VO2 max went up from 50 up to about 63. Right, so it went up significantly. So that means, right, her as an untrained person probably be better than most people who've been working out pretty hard for a long period of time. So, aerobic capacity is largely genetic, right, as well as most of this stuff, right? So, most of the stuff is like predetermined kind of stuff like that, right? So you either have, right? So if you don't have a lot of fast twitch muscle fibers, you're not going to be very explosive. You're going to be less explosive than somebody that doesn't do any type of training.
Is that fair to the sport? How there's like, genetically more hemoglobin?
It's not at all.
Right?
It's
So
not
they
fair at
can't
all.
do anything about it?
Nothing you can do about it. You're not taking any performance enhancing drugs to get there. Life's not fair.
Do you know how expensive that is to test that, like on the average?
Not that hard. You guys can do it here. You guys can do it over at the main campus for like $50. You guys can get a VO2 max test. There's a bunch of places where you can get a VO2 max test done now. Huh? What do they do for it?
Yeah.
So they put a mask on you that measures your respiration, and then they have you do an exercise test. Either on a bike or a treadmill.
Kind of like Galactica?
Huh?
Like Galactica?
Uh-huh. Yeah.
So is that what like athletes do when they get medical tests? They have that thing?
That's part of one of the things
Like when
they
they
do. Yeah.
transfer teams?
That's part of one of the things they do, yeah. So you can go get a VO2 max test done. VO2 max test is only really beneficial for people that are like really serious about their training. Like you can get a good approximation other ways from doing it, from other kinds of tests like that. So now if I'm, Cristiano Ronaldo, sure, like getting my VO2 max tested is important because I can get a 2 to 3% increase in performance through the proper training. A 3% increase in performance might be the difference between winning and losing. So it's very important. Questions? What questions you guys got about any of this stuff? Lab stuff for next week is going to be the muscles that we covered. muscles that we covered on Tuesday. Today's kind of just, kind of tell you guys a little bit more about like exercise and muscles and muscle physiology, exercise science and all that. So it's the appropriate like class period to answer those kind of questions. What questions do you guys have about all of that stuff? Exercise, training?
Here's that one.
Sure.
You know when people work out, they say you have to like train your CNS or you gotta rest your CNS?
Uh-huh.
Is that the motor unit you're talking about?
So yeah, so your nervous system, can become your nervous system becomes, activated when you do that, right? You need to give it adequate time to rest, right? So one of the good ways that we measure recovery is things like heart rate, right? So we can measure your resting heart rate. So it used to be a lot harder, right? So we'd have athletes the second they wake up, like they would take their pulse, right? And then we got those heart straps, and they would wear the heart strap to bed. Now most people have like, the Fitbit monitor, Fitbit or other kinds of things like that. So if your resting heart rate is going up, that means your nervous system isn't adequately recovered. Yeah. So yeah, you do need to give your nervous system a rest. So you can overstimulate the nervous system. So that's one thing. Yeah. There's a lot of science involved in like maximizing athletic performance, right? Getting in good shape, guys, not rocket science, not that hard to do, right? Avoid eating crappy food, right? Try to do something physically active 3 to 5 days a week, right? Not too much, not too little, right? That's, avoid junk food, don't smoke, floss on a regular basis, right? Not that complicated, right? But getting somebody in peak condition at a specific time period, that requires a lot of science, right? There's a lot of science involved in like getting somebody to peak for like the world championships in track and field, or
Do you think we're plateauing or no? Because if you look at athletes from the 20s, like even a high schooler now can probably beat them, with
We
all
can.
the science. Are
Yes.
we peaking, do you think, or no?
Well, I mean, we're always like hitting a new peak, yeah, so records always break. That's largely due to increases in performance, nutrition, training, all of those kinds of things, especially as the professionalization of sports has accelerated.
Right.
It's a lot easier for athletes to just focus 24/7 on being an athlete. Back in the old days, like even like baseball players back in the old days, most of them had a job in the offseason. Same thing with NFL and NBA players, right? They didn't make the kind of money they make now. So a good example would be like track and field, right? So back in the day, it used to be like centered tracks, right? So you literally would take wood and you'd burn it, and then that would make the track. So it was a track that was soft, so it would actually absorb more force. So the tracks today are actually designed to like maximize like your ability to get down the track faster. So Jesse Owens, right, guy that was the track and field star for the United States in the 1936 Olympics, totally like embarrassed Hitler. His world record in the 100 meters then was like 10.2 seconds, right? And we've actually calculated that if he'd done his sprint on a modernized track, he probably would have ran like a 9.8 100 meters, right? So that's part of it, right? So the professionalization of that, technology, training, like there's just so much more metrics we can like measure, observe, and take care of these. Our understanding of nutrition is a lot better than it used to be. We'll do supplementation, but really, honestly, the biggest is the performance enhancing drugs.
Is it
Who's your guys' favorite athlete?
Messi?
Huh?
Messi.
Messi takes performance enhancing drugs. They all take performance enhancing drugs. They all said that they don't. So here's a crazy thing for you. Okay, so testosterone, right? So testosterone is the granddaddy of performance enhancing drugs, right? So it increases. We'll talk about it a little bit more when we get into hormones, but right, increases protein synthesis, decreases catabolism, does all sorts of stuff that helps improve performance, strength, all that. Normal range, don't worry about what the numbers mean. Normal range for a man for testosterone is between 300 and 1200, right? In Major League Baseball, they don't even test you for performance enhancing drugs unless your testosterone is above 1800, which is literally about, so the average, you take your average college age guy, he's probably got a testosterone level about 600 to 700. We're talking almost 3 times what the testosterone of the average guy before they even like start doing testing, which means most of these guys are taking low levels of some type of performance enhancing drug.
Is that genetics, the basal?
Genetics, yeah, but like you're talking like 1/10 of 1% of the population can be naturally above 1200 nanograms per deciliter, right? But which is not most of these guys. Most of these guys are taking low levels of something. Same thing with like actors, like, you know, don't get me wrong, I love Chris Hemsworth, like he's great, but I 100% guarantee he takes stuff to get as big as he gets for Thor. So yeah, drugs are really the biggest like change for a lot of these people. What other questions you guys have? Nothing else?
So, I have a personal question, kind of.
Yeah.
My right shoulder has been messed up. how could I strengthen that? Do you think, or like, because so what happens is when I laterally raise it, it cracks. It doesn't hurt though.
Yeah.
It just cracks.
Something muscularly is out of whack and it's causing your glenohumeral joint to not glide properly. So my best advice would be go see a physical therapist to get it identified.
See, I was trying to get that information for free.
Yeah, so that would be my best advice, would be talk to a PT and
And so how do you get those deep muscles in the back of the shoulder, like these ones?
like the rotator cuff muscles?
Yeah.
So doing rotator exercises.
So
Yeah, that'll help strengthen those rotator cuff muscles, yeah. So, but yeah, fortunately, yeah, I would recommend that you talk to a physical therapist about that. Any other questions, guys? No, all right, so lab quiz on Tuesday is gonna be over the muscles that I covered on, last Tuesday. So I'm just gonna point to a muscle, you identify what the muscle does, or give me a muscular action for the muscle. Okay, so make sure you know the muscles and the
Not
muscle
the name.
Well, the name of the muscle, yeah.
you want to.
Yeah, so know the name of the muscle and then give me an action for it. So like biceps brachii, action, flexes the elbow joint, right? Pectoralis major, right? Flexes adducts the humerus. Yeah. Tough, guys. This is, I told you guys first day of class is gonna be one of the harder classes you guys take throughout. You know, I mean, I've got 2 master's degrees, and I'll tell you one of the hardest classes I took was this, physics, and biochemistry. Were probably the 3 hardest classes I took, you know, at any level of college.
This is easy.
So, all right, guys, have yourselves a good weekend.